All right, so couple of things. I have your graded exams up here. The class average was like a 72, which isn't so bad at all. For one of my tests, that's usually about a letter grade higher than what it comes out to be, so that's good news. I would like to have your next exam next Friday. So 1 week, no, excuse me, not next Friday, next Thursday. So 1 week from today. And that exam will cover induction machines and synchronous machines. So you have had two homeworks on induction machines to this point, and I did update the second homework set to include the answers to all the problems and all that kind of jazz. I'm going to work on getting up a homework set on synchronous generators tonight that will be due on Tuesday, and then a set on synchronous motors either tonight or tomorrow that will be due the following Thursday. So the same day as your test, so that you should do it to help study for your test. For the last exam, I allowed you guys to have one equation sheet front and back. I think this time I'm going to allow you to do open notes. For those of you that take your notes on a computer, that means that you need to have a printout, because I can't let you just be on your laptop and Google all kinds of stuff while you take your exam or whatever. So kill a couple of trees, print out all your notes. I am in the process of getting your homeworks and all that kind of stuff graded. I don't know how many of them will be graded before the drop date, but your test is graded and that's a much bigger part, so you're probably more interested in that anyway. All right. So any questions before we start talking about what we're supposed to talk about today? Oh, turning on the system so that you guys can see it would probably be of use.
Just to clarify, is the test the 9th or the 7th?
I have to look at a calendar, because I don't know what day today is. The 9th. So your next exam in this class will be Thursday, the 9th. Next Tuesday's class meeting will just be used as a review session. So you can ask any questions you want about any of the homework problems, any of the examples, any of that kind of stuff. And then when you're done asking me questions, we'll wrap it up for the day. And then after our exam, we will cover DC machines, and then we're done. All right, so let me see what's going on in chat here. Yes, I will be uploading the exam grades to Moodle at some point this afternoon. So in our last class meeting, we talked about the operation of synchronous generators. Sorry, now I'm writing generators down. Today, we are going to talk about synchronous motors before developing power and torque relationships for synchronous machines in general. So our discussion of synchronous motors is going to be pretty brief because any synchronous generator can operate as a synchronous motor. And since we have a good understanding of how synchronous generators work, synchronous motors are going to be pretty straightforward, right? So in a synchronous generator, we had induced current flowing out of our stator terminals, right? So for our equivalent circuit, looking only at the armature side, we had EA connected in series with some resistance RA, connected in series with some resistance or reactance, excuse me, JXS. This was our terminal voltage, V phi A, like so. and the direction of our current was to the right, so flowing out. So this is the generator equivalent circuit. Over to the right, I'm going to draw the motor equivalent circuit. And there we have it. It is literally the exact same thing, except our current is flowing in the opposite direction because we're taking in electrical power and converting it into mechanical energy, whereas with our generator, we were taking in mechanical power and converting it out to electrical energy, okay? So we can write a simple Kirchhoff's voltage law equation around this loop, and we'll find that our terminal voltage V phi A is equal to EA plus IA times RA plus JXS, and that effectively governs how this thing behaves, all right? So in a synchronous motor, once again, we expect our rotor field to be rotating at the exact same speed as our stator field. So everything is just operating at our synchronous speed ns. However, there is a large fundamental difference between an induction machine and a synchronous machine. And that is that induction machines are self-starting and synchronous machines are not. Meaning that if we applied some three-phase voltage source to this side of this thing, and we applied a DC current through our field winding, we shouldn't expect the rotor to spin. In fact, what we will see is that the rotor will vibrate back and forth because the average torque that's produced is zero. Effectively, what's going on is that the stator field is revolving so fast that the rotor can't catch up, okay? So for half of the cycle, it's producing a torque in a clockwise direction. The other half of the cycle, it's producing a torque in a counterclockwise direction, and the rotor is just going to wiggle. That's all it's going to do. So we have to input some energy to get it to spin first, and then it'll catch up. So let's talk about how that's done, okay? So we can start now. Let's put starting with a variable frequency supply, okay? So we can effectively put a power conditioner in between our supply and our motor. So this black box right here is going to represent a frequency converter. Okay. Over here on the left-hand side is our three-phase supply. And what this frequency converter allows us to do is we have control over what frequency we're applying, and we have control over what voltage we're applying, right? So what does it mean that we have control over the frequency? Well, since we know that the synchronous speed of a motor
is proportional to the frequency, right? NS is equal to 120 pi, or excuse me, 120 F over the number of poles, same exact equation we've been using. If we start with a very low frequency, that means our stator field is rotating very slowly. And if our stator field is rotating very slowly, it's easy for the rotor to catch up. And then we can gradually adjust the frequency, increasing it. And slowly but surely, the rotor will continue to catch up over and over and over again until it reaches whatever desired speed we have. So we have frequency converter here. And then this is connected to the input terminals. Of our synchronous motor. The input to our synchronous motor is our current I1 and our DC field count, right? So once we've effectively caught up to the speed that we want, then we can apply an excitation in our field winding. And our field poles will lock with our stator poles and our rotor will spin at the same speed as our synchronous field is rotating, okay? So this is starting with a variable frequency supply. Effectively, we started at a very, very slow speed and then gradually bring it up to the speed that we want. This is the method that's used particularly when we want our motor to be able to spin at multiple speeds, because we can control the speed by changing the frequency that we're applying to our motor, okay? The largest drawback of this particular starting method is the cost. The frequency converter is an expensive piece of power electronics, so it's not something that can easily be, purchased and thrown away. You have to take care of it and all that kind of good stuff. And it really only provides a benefit if you want to be able to control the speed of your synchronous machine, right? So you want to have direct control of it. Another way to start them is as an induction machine. So effectively, in this case, let me make sure I spelled this correctly. An amortisseur or damper winding is added to the shaft of our machine. So this winding is effectively putting a small squirrel cage on the rotor of our synchronous machine, such that we can induce rotation, because we know that in an induction motor, we have a non-zero starting torque that can get it to start spinning. And then once we get close to synchronous speed, we then turn on our field winding and that'll kick it back up and we'll lock in, okay? So an amortisseur or damper winding is added to the shaft. The field winding is unexcited, meaning we don't apply a field current. And induction causes a torque which gets the rotor spinning, when our rotor speed mm is approximately equal to our synchronous speed the field winding is energized such that the rotor spins at our synchronous speed. So what happens to the damper windings when we're at synchronous speed? You guys take a stab. All right. So the purpose of the damper windings is to produce a torque through electromagnetic induction, right? Well, if our rotor is spinning at the synchronous speed, how much current are we inducing in our damper windings? Exactly right. So if they're spinning at the same speed, it's zero. So effectively, once our rotor starts spinning at the synchronous speed, the damper winding doesn't do anything, okay? Now, if we happened to change the loading of the motor while it was online, which could cause our motor to slip out of synchronicity, that damper winding will actually be able to produce a torque to get it to catch back up. So effectively, it's feedback control that will always make sure that our rotor catches back up to our synchronous speed during operation. So the overwhelming majority of synchronous rotors actually have some form of damper winding in there to be able to handle transients, changes in loading and things like that that would cause it to slightly slow down. That damper winding catches it back up. Okay. So if I were to ask you guys on your exam, what a fundamental difference between induction motors and synchronous motors were, here is what I'm expecting to hear. Okay. Induction motors are self-starting. Synchronous motors are not. Induction motors have some amount of starting torque. It's not a lot, but it is enough to get the rotor spinning. Synchronous motors have zero starting torque. Okay. Synchronous motors, the rotor spins at synchronous speed. And in an induction motor, the rotor spins at slightly less than synchronous speed. And that amount of difference, if you recall, is what we call the slip. And the slip tends to increase as we load the rotor. All right. So now let's talk about, can I go to the next page, or are you guys still writing stuff down? Power and torque relationships. Okay. So I'm going to draw a power flow diagram, much like we did for our induction machine, but I'm going to draw two of them. One of them will be for generator operation, and the other one will be for motor operation, right? So when we have a synchronous generator, our input power is the power that is applied to the shaft. So we actually have something physically connected to the shaft that is causing it to spin. So we have some form of mechanical power causing our rotor to rotate. That's our input. Second here. Then we are going to have our friction and windage losses. So this is PFW. We might also have stray, but we've been neglecting them, so let's just continue to do so. Then we're going to have our field losses. So this is effectively the copper losses in our field winding. So I'm going to call this PFCU. And now we are at our air gap. So let's call this PAG. We're on the stator side of the machine now, or the armature side of the machine. So we have our core losses, just like we had in an induction motor. Then we are going to have our armature copper losses. PACU. And at the output, we have the electrical power that's being provided to our load. Okay. For our motor operation, it is literally the exact same diagram, except in the opposite direction. Okay. So on the left-hand side, we're going to have our electrical input power. We're going to have our armature copper losses. Our core losses. We're at the air gap now. We have our field winding losses. Then our friction and windage. And assuming our stray is negligible, the output here the power delivered to our shaft. So very, very similar power flow diagram to what we saw with induction motors, but now it can go both ways because we have two viable modes of operation. Okay. So now let's throw some math at this. What's slightly too far? All right, so sure. You guys good? All right. So in a synchronous generator, our power input of the system is the prime mover, which rotates the shaft. So we can say that our shaft power is simply the torque that is provided by the prime mover. Let's call this T shaft actually, times omega m, which is the speed, the angular velocity of our rotor. And since our angular velocity of our rotor is the same thing as the angular velocity of our stator field, we can also write this as T shaft times our synchronous frequency. Okay. The power that's internally developed from converting mechanical energy to electrical energy. So this is essentially the air gap power. It's technically slightly different. It's the air gap power plus friction and windage losses, but we're going to wind up ignoring it in a minute anyway. I'm going to call this PD. So this is going to be the developed power. Is the developed torque times omega s. And this is also going to be equal. So this is where our electromechanical energy conversion comes in. Equal to the magnitude of 3 times the magnitude of our induced voltage times the magnitude of our armature current times the cosine of this angle capital Phi, okay, where the angle capital Phi is theta plus delta. Theta is simply the angle of V phi A minus the angle of IA. So that's our conventional electrical angle, okay? So the phase difference between our voltage at our terminals and the current flowing into or out of our terminals. So that's an electrical angle. And then delta is the power angle that we talked about in the last class, which is the difference between the angle of EA and the angle of V phi. You raising your hand? Yeah, what's up? PD for developed power and developed torque. Okay. So effectively, this is what's happening internal to the machine. So not at the input side, not at the output side, but in the middle in that electromechanical energy conversion process, okay? So it's related to the torque the speed, the induced voltage, the current, and then the phase angle between those quantities. Okay. The electrical power, sorry, go ahead.
I think I'm just confused, but it has, omega M is equal to omega S times 1 minus S.
Right, so that is for an induction machine where we have a slip. In a synchronous machine, by definition, the rotor is spinning at the synchronous speed. So omega M and omega S are the same thing. So we're talking about two entirely different machines here. Right, so induction machines is what we covered up to last week. Now we're talking about synchronous. Okay. So just to be real clear here, on the exam, I'm going to tell you, you have an induction machine or you have a synchronous machine, so that you will know what it is that you are dealing with. Okay. All right, and now let's develop a relationship for our electrical power. So this is a three-phase machine. So it's going to be 3 times the magnitude of the voltage at the terminals of the machine times the current, magnitude of the current flowing into the terminals of the machine or out of the terminals of the machine in the case of a generator. Cosine theta, where theta is just the angular difference between the terminal voltage and the current flowing into the terminals, right? So we have 3 different angles that we have to pay attention to, not really, because the third one is just the sum. We have a power angle that relates our induced voltage to our terminal voltage. And then we have our electrical angle that relates our terminal voltage to our terminal current, right? So theta is the voltage that you've been dealing with ever since you learned about steady state sinusoidal power. Delta is that power angle that's related to the torque of the machine. We'll see that in a moment. Okay. So these are effectively our power relationships. We are going to play around with them a little bit here, okay? So for synchronous reactances that are much greater than our armature resistance, which is effectively every synchronous machine we can ever have, our power relationship, P in general here, well, I'll talk about that in a moment, is going to be 3 times the magnitude of our induced voltage times the magnitude of our terminal voltage divided by our armature reactance, or synchronous reactance, excuse me, X sub S sine delta. So what this represents is really the air gap power, the developed power, and our output power, depending on which side we're on, when we neglect our core losses, or excuse me, our copper losses of our armature, okay? So this is kind of a all-purpose power relationship that relates all the different things, okay? So when delta is equal to 90 degrees, our sine function reaches its maximum. So we can say that the maximum power is 3 times EA over V phi A divided by our synchronous reactance. Our developed torque is going to be P divided by omega S Okay, so this is the torque that's being applied to the rotor. And it is just the power that's being delivered to the rotor divided by the angular velocity. That's the relationship between power and torque. So it's going to be the exact same equation we have above, except there's going to be a factor of omega s in the denominator. And from this, the maximum torque we can develop occurs when delta is equal to 90 degrees. So that's just going to be 3 EA B phi A over X sub S times omega S. And that is all I expect you guys to know about synchronous machines. Okay, so we're going to spend the next several minutes working a couple of example problems. Nothing as brutal as that one that had 14 steps or whatever that I made you guys suffer through last week. All right, let me know when I can go to the next page and we can start throwing some actual math at this. All right. One of you shook your head and I assumed he spoke for all of you. Apparently I was mistaken. We good? Casey, okay? All right. All right, so here's our first problem using these relationships. We have a three-phase, 100 horsepower, 60 hertz, 480, 277Y volts RMS rated 4-pole synchronous motor. And it has an armature reactance, an armature resistance of RA is equal to 0.15 ohms. And a synchronous reactance of XS is equal to 2 ohms per phase. Okay. At the rated load, meaning we are generating 100 horsepower, or our power at our shaft is 100 horsepower. And a leading power factor of 0.8. The motor has an efficiency of 0.95. We are going to determine the maximum torque developed by the motor. Okay. All right, so what I'm about to write down is nothing more than our equation for maximum developed torque. Tmax is equal to 3 times the magnitude of the induced voltage times the magnitude of our terminal voltage divided by XS times omega S. So let me ask you guys what I hope is a simple question. Which of these things do we know from the problem statement? All right, so XS is given to us. That's 2 ohms. I agree with that wholeheartedly. Pardon? How do we know omega S? So omega S is the angular velocity. So that's going to be something measured in radians per second, which is very much not horsepower. Sorry, what? We can find omega S. I agree with that wholeheartedly. We'll do that in just a moment. But what's the other thing in this equation that we know? We don't know EA, that's the induced voltage, because that's the thing that can change to make this work at a particular level. We know our terminal voltage, right? So V phi is going to be a constant. That's our rated voltage. Okay, that is the thing that is not going to change. And then EA is going to be higher or lower than V phi, depending on if we need to overexcite or underexcite our system, right? So V phi A, or at least the magnitude of it, is 277 volts RMS. So when we're given a voltage rating, we are given that V phi quantity, right? And because our equivalent circuit is on a line to neutral perspective, we need to use the Y voltage, not the delta voltage. Okay. So it was suggested that we can solve for omega S. I agree with that wholeheartedly. Right? So omega S, the synchronous angular velocity, is related to our synchronous speed, right? What's the conversion factor? We use this at least the last 3 class meetings. 2 pi over 60. Great. So what I'm going to do is I'm just going to put in my equation for our synchronous speed, which was 120 F over the number of poles. Multiply this by 2 pi over 60. And this is going to look like 4 pi times our frequency divided by the number of poles. So that's going to be 4 pi times our electrical frequency of 60 hertz divided by 4 poles, comes out to be 60 pi or 188.495 radians per second. Okay. So we know this, we know this, we know this, and 3 is just 3, so we know that as well. So now the only thing that we have left to figure out is how to determine that quantity EA, the magnitude of our induced voltage. Okay. So let's look at the equivalent circuit. since we are dealing with a motor, our current is flowing into the system instead of out of the system, right? So we could say that EA is going to be V phi A minus IA times RA plus J XS. Anybody have a problem with that Kirchhoff's voltage law equation around this loop? Fairly straightforward. All right. So let's assume V phi A is 277 angle 0 degrees. Right, so we're just assuming that our terminal voltage for the A phase is at 0 degrees, and then we're going to let everything else work itself out. Okay. We know what RA is, we know what XS is, so really the only thing we need to figure out for this equation is that current. Anybody have any thoughts on how we might relate what we are given to that current? Use the horsepower. Okay, so we're going to use the horsepower, but we're also going to use the efficiency, right? Because the efficiency in this case, we have a generator, or excuse me, we have a motor, right? So our efficiency is going to be the ratio of our mechanical power at the output divided by our electrical power at the input. And our electrical power is related to that current, right? So we can say that electrical power is going to be equal to the mechanical power divided by our efficiency. That makes sense to everybody? Anything wild or crazy there? All right. So now, how do we relate our electrical power to that current IA? Well, it's a three-phase system, right? So our electrical power is going to be 3 times our terminal voltage times our current times our power factor. Anything wild or crazy here? Nope. Okay. So rearranging this thing, our current is going to be our mechanical power divided by 3 times our efficiency times our terminal voltage times our power factor. I believe I got everything taken care of there. So that's going to look like 100 horsepower. There are 746 watts per horsepower. 3 times 0.95 times 277 volts times our power factor of 0.8 gives me a current of 118.120 amps RMS. But in order to figure out what EA is, I need the actual full RMS phasor representation of my current here, right? So I need more than the magnitude, I also need its phase angle. Well, how are we going to figure out its phase angle? Exactly right, the inverse cosine of the power factor, okay? So the angle of IA is going to be the inverse cosine of our power factor. So that is going to be the inverse cosine of 0.8 which comes out to be 36.87 degrees. Is this angle supposed to be positive or negative? So this is the angle of the current, okay? So it's not the angle of the complex power, it's the angle, so the angle of the complex power is the angle of the voltage minus the angle of the current, right? Well, the angle of the voltage is 0, right? So we would expect theta minus, or excuse me, a 0 minus the angle of our current to be a negative number to give us a leading power factor, which means the angle of our current has to be a positive quantity because 0 minus a positive number gives us a negative number. Does that make sense? Okay. So because our power factor is leading, 0 minus this angle has to be negative, which means this angle has to be positive. From here, EA is just 277 angle 0 degrees volts RMS minus 118.120 angle positive 36.87 degrees amps RMS times 0.15 plus J 2 ohms. And I get 451.139 angle negative 26.263 degrees volts RMS. The magnitude of EA is just this part right here. And so my torque that I'm looking for is 3 times that 451.139 volts times 277 volts divided by 2 ohms, which was excess. And then that 2 ohms is multiplied by 188.495 radians per second. And so this is going to give me 994.447. I'm just going to play around with the units here to show you that this is going to give you torque. But I expect you guys to just put this in Newton meters in a moment, right? So I have units of volts, this thing will draw, times volts over ohms, which is a volt per ampere, times radians per second, right? So this volt and this volt is going to cancel out. So this looks like volts times 1 over amps. So that's a volt times an amp. Times 1 over seconds, which is just multiplied by seconds. So I have volts, amps, seconds, which is watts times seconds, which is joules, which is the same as a Newton meter. Okay. So 994.5 Newton meters is our maximum torque developed internal to our motor in this case. So let's work a similar problem from a slightly different perspective, okay? Can I go to the next page? Trying to be nice and not scoot ahead. Okay. I'm getting a thumbs up from Hugh, so blame him if I move too quickly. All right, so we have another 3-phase synchronous motor, right? This motor is rated for the electrical input power. Okay, so in the last example, our rating gave us the mechanical output power effectively. This time we're looking at electrical input power. Operating at a frequency of 60 hertz, rated for 480 277Y connection. And it has 6 poles. So we have an armature resistance of RA is equal to 0.09. Excuse me, I didn't put enough zeros in there. And a synchronous reactance of excess is equal to 1.5 ohms per phase. Its friction and windage losses are 2.46 kilowatts. Its core losses are 1.941 kilowatts. And its field losses can be neglected. If the motor operates at a power factor of 0.85 lagging, I want us to determine the motor's efficiency and output torque at full load. Okay. So we are asked to define the, or to determine the motor's efficiency. So let's write something down here. So the efficiency of a motor is going to be the output mechanical power. So let's call that P shaft divided by the input electrical power. Okay. The output torque is going to be our output power provided at the shaft divided by the speed at which the shaft is rotating, which is our synchronous speed in a synchronous motor. Okay. So we need to figure out what P electric is, we need to figure out what P shaft is, and we need to figure out what our synchronous angular velocity is. So let's choose the lowest hanging fruit here. Probably that synchronous angular velocity, because we've done it over and over and over again. So that's going to be something easy to take care of, right? So omega S is NS, our synchronous speed, times that conversion factor of 2 pi over 60, which is going to look like 4 pi F over the number of poles. That's the relationship that we developed in the last example problem, so I'm just using it again. Okay. So in this case, that's going to be 4/6 times 60 pi And I didn't actually ever write down the number, so let me do that really quickly. Forty pi, 125.664. Radians per second. Okay. So that part's taken care of. So we're arguably a third of the way there. It's really closer to like a fifth of the way there, but that'll be okay. All right. So we're given a bunch of powers here, right? We're given friction and windage losses. We're given core losses. So let's go back up here and let's look at that power flow diagram that we kicked things off with, right? So we're dealing with a motor. And we can see that our shaft power is nothing more than our electrical input power minus the copper losses due to our armature winding, minus the core losses, minus the field losses, minus the friction and windage losses. We were given core losses. We were given friction and windage losses. So we have to figure out what that quantity is. And we have to figure out what that quantity is. If we know the electric power in, the losses in our armature windings, and the other losses, we can figure out whatever's left must be the power that's delivered to our shaft, right? So let's start with our input power. How are we going to solve for the input power of this system? So this is electrical power, actually. So let me write that down specifically as electrical power. So that's going to give us some clue as to what kind of relationship the what in the problem statement. Oops, that is definitely the wrong page. Sorry. So P electrical is going to be something. So you asked about us using the complex power. So what do you mean by that specifically? Because the short answer is yes, but I'm lazy and I want to be as lazy as possible. Okay, so P here is the real part of the complex power, right? So what in our problem statement is related to complex power? The 100 kilovolt amperes, all right, so that's the magnitude of our complex power, also known as the apparent power. Okay, so that's definitely something. What else? Power factor, absolutely. So if we have the apparent power and we have the power factor, what happens when we multiply those two guys together? We get average power, which is exactly what we're looking for, right? So the electrical power at the input here is going to be nothing more than our apparent power, the magnitude of our complex power, multiplied by our power factor. So 100 megavolt amperes times 0.85 is going to give us 85 kilowatts, because we're looking at the real part, and the real part of complex power is measured in watts. Sean, what was your question? Excuse me, kilovolt. Kilovolt ampere is giving me kilowatts. Sorry about that. All right. So we just figured out what our electrical power is. Okay. Our friction and windage losses are given, our core losses are given, so now we need copper losses. How do we calculate copper losses? In a three-phase system. How do we do it for an induction motor? Sorry, what? Copper losses. What do you think it is? You've gone back 11 pages in your notes or so.
3 times the current squared times R1.
Exactly right. 3 times the current squared times the resistance, because we're just trying to find what power is absorbed in our windings, right? So in this case, it's going to be 3. So we're looking for P A C U. That's going to be 3 times the magnitude of IA squared times RA. Well, we got a little bit of a problem here because we don't know what the magnitude of IA is. But I would argue that we know how to calculate it because we did it a couple of minutes ago, right? So if we know what our power is and we know what our terminal voltage is, we should be able to figure out what our current is, right? So as a quick aside here, the magnitude of IA in a three-phase system like we have here is just going to be the magnitude of our complex power divided by 3 times the magnitude of our terminal voltage, right? So apparent power is just 3 times terminal voltage times current. So if I solve for this quantity IA, that's going to look like 100 kVA over 3 times 370, 277 volts. Which comes out to be 120.337 amps RMS. So substituting that in up here, we're going to have 3 times 120.337 amps RMS quantity squared times our resistance, which was 0.09 ohms. Gives me copper losses of 3.910 kilowatts. Looking at our power flow diagram, our output power is nothing more than our electrical power minus our armature copper losses, minus our friction and windage losses, minus, excuse me, that should be a P, our core losses, which means we have 85 kilowatts minus 3.910 kilowatts minus our friction and windage losses, which were 2.46 kilowatts from our problem statement, minus our core losses of 1.941 kilowatts. So the power at our output is 76.689 kilowatts. From this, our motor efficiency, 76.689 over 85, looks like 90.222%. And our maximum torque, excuse me, not our maximum torque, our shaft torque is going to be the power at the shaft divided by the speed at which the shaft spins. 76.689 kilowatts divided by 125.664. 125.664 radians per second gives me 0.610 kilonewton meters, or 610.271 newton meters of torque. All right, I believe that is enough of me making you guys suffer for today.